Welcome back, everybody. So in our previous videos, we've talked about substitution and how all that works. And we did a whole lot of examples to get good at doing it. So in this video, I want to show you some substitutions that will lead us to new derivative rules or new integral rules. Things that when you take Calculus 2 especially, you'll use constantly. So let's get started. So how would you integrate tangent? That's a great question because if you think, the derivative of what is a tangent, right? Well, it's not tangent, right? It's not cotangent. It's not secant, although it's closer because the derivative of a secant would be a secant times a tangent, but it's not just a tangent itself, so that doesn't quite work. So what is an antiderivative for just a tangent by itself? Well, this is something that we'll have to have memorized, and I'll show you where it comes from. So the trick is to take tangent and make it a fraction. So let's rewrite tangent of x as sine of x over cosine of x. And now this looks like something suitable to be substituted, right? If we let u be the cosine, the stuff in the denominator, its derivative is negative sine, right? So that's perfect. I can replace tangent with sine over cosine, then I can replace the cosine with a u and that sine of x dx with negative du. And the reason that this jumps out at me is because I remember I've done so many examples and because I'm so used to working with my derivative rules that if I have 1 over u, when I integrate that, that's an integral I can do. It's log of absolute value of u. And again, so if it's not obvious to you, what to use to substitute for what, the first step is go back and make sure you know your derivative rules absolutely cold so that you will recognize what you can integrate when the need arises. So I get negative log of absolute value of u, which I can then turn the u back into cosine of x, so I get an answer in terms of x's. But that's not the form that in Calculus 2, for example, I would tell you to have memorized because, well, to me it just looks unpleasant. All right, so the thing is, what's the derivative of a tangent? Remember the rules. Derivative of a tangent is a secant squared. Derivative of a secant is secant tangent. So why is it that when the derivatives for secants and tangents have secants and tangents in them, why is it that all of a sudden the integral of tangent is like a negative log of cosine? That's just weird. So I think there's a better way to write it, right? At least a way that fits the rules and easier to memorize. And you do a little bit of algebra tricks, right? What you could do is take that minus sign in front of the log, and remember, a minus sign in front of the log, you can bring up and make it an exponent. Again, there's no calculus here. It's not a derivative or an integral thing. This step is just using algebra log rules. Take that minus 1 in front of the log and make it an exponent. So this is cosine all raised to the minus 1 power. Now notice this isn't inverse cosine, right? It's the cosine of x all raised to the minus 1 power. In other words, it's 1 over cosine of x. Oh, well, 1 over cosine has a name. It's secant. So this fits the pattern, right? Because it makes perfectly good sense that the integral of a tangent ought to have something to do with secants. And it does. The integral of tangent is log of absolute value of secant of x, plus c, of course. Okay, that's important enough that it's a rule you should just know. And in Calculus 2, the very first day, we hand out a list of rules you should just know, and that's one of the most important ones on the list. All right, what about cotangent? Well, this is going to work almost exactly the same way. What we'll do is replace cotangent with cosine over sine. Okay? Then we play the same game again. Let u be sine of x, du would be cosine of x. Oh, that works even easier because there's no minus sign to worry about. So cotangent of x becomes cosine over sine, which when we do the substitution becomes 1 over u du. So when you integrate that, that's a log of absolute value of u. Now I substitute back in the answers and I get log of sine. Now, Okay, that's an answer. But all of a sudden now cotangent, and now I got a sine, right? Shouldn't there be like a cosecant somewhere? Well, well, yeah, there is. What you could do is put a minus sign in front and another minus sign in front. Those two cancel each other out. So obviously I haven't changed the problem. What I'm going to do is leave one of those minus signs in the front. The other one I'm going to use as an exponent on the sign. So that makes it parentheses sine of x, all raised to the minus 1 power. That, of course, flips the sign, sin, and makes it 1 over sine of x. And, of course, 1 over sine of x, that's cosecant. So I still have a minus sign outside, because I left one of them there. Log of absolute value of cosecant of x. And, of course, that fits the pattern perfectly, because an integral of a cofunction, right, you'd like to have a minus sign floating around in there, because this was a cotangent. You ought to have a minus sign there, and you do. When you integrate cotangent, you get minus log of absolute value of cosecant plus c. So again, that's another thing that's an important rule for us just to know. Integral of secant of x. So you might think, oh, okay, this is good. I could make, well, I don't know how to do anything else with it. Let's make it 1 over cosine and hope that works. But it doesn't, because when you do 1 over cosine, what you get is just 1 over cosine. There's no sine next to it that I could use to be part of the du. So there's a trick, okay? What you want to do is take this secant and multiply it by this weird looking fraction, okay? Again, I'm not going to claim this is obvious at all, just that it works and gives us a cool formula. So if I multiply this secant by secant of x plus tangent of x over secant of x plus tangent of x. Of course, that fraction is just 1, so I haven't changed anything. But it changes the look of our integral in such a way that it'll make this much easier to do. So let me show what I mean. We'll multiply this secant through the top, right? This will become secant squared, secant times secant, plus secant times tangent. And all that's over secant plus tangent. And you think, okay, why is that going to help me? Well, look, the top is the derivative of the bottom. If I let u be the denominator, secant plus tangent, then its derivative is, sure enough, the derivative of tangent is secant squared, and the derivative of secant is secant tangent. Now it's in reverse order, obviously, because of the plus, because of the way we wrote it above. But the numerator is exactly the derivative of the denominator, which means if I do u substitution, I just have 1 over u, du to integrate, which means I have log of absolute value of u. That's awesome. That gives me log of absolute value of secant plus tangent, of course, plus c. Now, why do I especially like that? Well, what's the derivative of a secant? Secant times tangent. So see, it makes perfectly good sense that the integral, okay, it's got a log, but so did the integral of tangent. But instead of just having a secant, look what the log is of, a secant plus a tangent. That's a plus, not a times, so it's not perfect, but it does look a lot like what you would expect from the derivative